Showcase, a glimpse of science in the next century. Path of least resistance, sleuthing superconductivity's secrets. Renaissance renewed, a classroom at the crossroads. Ripples from the chasm, probing the wrinkles of space-time.
SIGGRAPH 92 just broke records this morning. We have over 31,000 attendees.
This is the Olympics in our area.
From the atom to the universe, it's all here.
Chicago, Illinois. The international computer graphics community gathers at the McCormick Place Convention Center for SIGGRAPH, their annual conference on the state-of-the-art in tools, techniques, and applications. But one exhibit stands apart at this year's conference, Showcase. Created by the pioneers in high-performance computing and communications, or HPCC, Showcase provides a unique glimpse at science as it will likely be done in the 21st century. Represented in force at Showcase, the National Science Foundation Supercomputer Centers.
We have an opportunity in an organized fashion for a week show to bring something like Showcase, in which 36 scientific projects from all over the country can now come through the network and appear to be in McCormick Place. Even though the scientific instruments are in Minnesota, California, North Carolina, you walk into Showcase, hey, it's all here. And that's the magic of the network.
Thanks to high-speed fiber optic links connecting McCormick Place to national computer networks, the Showcase exhibits enable the audience to peer into phenomena across almost every scale. Like journeying across an atomic surface imaged in real time by a scanning, tunneling microscope, navigating through the motions of giant molecules, visualizing sound waves breaking up a kidney stone, or simulating a thunderstorm that could spawn a deadly tornado. Then from a vantage point high in space, peering down at the giant waves propagating from an earthquake beneath the Pacific Ocean, or traveling far beyond our planet to the beginnings of the cosmos itself. Simulated on remote supercomputers or created from data gathered by faraway instruments, these visualizations demonstrate the power of distributed computing, doing computation where the resources are and not necessarily on a single machine.
In a few years, the network is the computer, and it doesn't matter where your supercomputer is, it doesn't matter where your data resources are, where your sensors, your scanners, or your satellite data. It can come from anywhere, it can be stored anywhere, but you can access it at your fingertips on your desktop.
What we're going to do right now is to actually use the Cray YMP at NCSA down in the middle of Illinois.
For example, researchers linked to a supercomputer at the National Center for Supercomputing Applications demonstrate how distributed computing techniques can be utilized to evolve a thunderstorm model and change the parameters in real time. Computation is not only essential for simulating reality, but also for measuring it and processing and visualizing the vast amounts of resulting data. By obtaining the output of instruments in real time, scientists will increasingly be able to control, even steer instruments from anywhere in the country and eventually the world. One example, a team from the San Diego Supercomputer Center and nearby research institutions created a prototype distributed computing environment to control an electron microscope in San Diego, where nearby supercomputer processes the resulting image data.
Hello, Chicago. Chicago, are you there?
It looks good here. Can I go ahead and translate?
From a workstation in Chicago, a scientist interacts over the network with a technician in San Diego, requesting that the sample be rotated or a yet tinier portion be probed in real time.
Yes, we've got the image here. Looks very good.
Then a 3D representation can be called up and animated. From the structures within a single nerve cell to the anatomy of the brain, distributed computing permits complex medical images to be explored remotely. Here, magnetic resonance images of the brain computed at the Pittsburgh Supercomputing Center are displayed and manipulated locally on a low-cost workstation.
The model of a human being, a scientist sitting at a computer alone, has to go away. We have to have collaborative efforts involving many scientists working with collections of computers. And we have to develop the technologies and the techniques and the sociology to go along with group activities.
Linking together both instruments and researchers creates opportunities for scientific collaboration on a scale as never before. Without doubt, the need for such collaboration is growing in proportion to the complexity of the problems to be studied. But with growing torrents of data from supercomputers and instruments, how can scientists make sense of it all? New kinds of human and computer interfaces, such as virtual reality, are necessary to turn all the data into shared knowledge. For an exhibit that really caught the crowd's imagination, little could rival The Cave. Here, spectators could share the experience of total immersion in a virtual environment, complete with sound and 3D images.
Virtual reality is a mode of scientific visualization. It's something that lets you get inside of the data. Now, most computer screens, you're outside looking in. In this, you're inside looking out. In The Cave, you can really have an expert navigator, like a guide in the jungle, and somebody who's the research scientist who knows what to look for in the data. They don't have to be the same person.
But beyond the excitement of virtual reality are its serious scientific applications: designing molecules, predicting the weather, mapping the galaxies in the cosmos. These are but some of the grand challenges of science and society.
There are the grand challenges of science, the grand challenges of our society. If we're to remain competitive in the remainder of the 20th century and on into the 21st century, and in fact to improve our competitive position, we will have to learn how to use the most advanced technologies.
In some sense, you could say searching for superconductivity is a metaphor for my scientific career.
For much of his 40-year career, University of Illinois physicist David Pines has struggled to understand the physics behind superconductivity. Ordinary metals exhibit some resistance, which inhibits the flow of electricity and causes loss of energy in the form of heat. Superconductors are different. They conduct electricity with no resistance whatsoever. But before these materials can become superconducting, they need to be cooled below an extremely low temperature called the transition temperature. Typically, this occurs near minus 258 degrees centigrade, a temperature at which helium liquefies. Although scientists had known about superconductivity since 1911, by the 1950s, many of the greatest scientific minds had tried and failed to develop a viable theory of superconductivity.
This was the biggest unsolved problem around in fundamental physics. How on earth was it that these metals would develop a transition to the superconducting state at these low temperatures?
In 1952, David Pines came to the University of Illinois to take up the superconductivity challenge, working as the first postdoctoral research associate of the legendary physicist John Bardeen.
John came here because he wanted to be free to work on superconductivity. It was his consuming passion. He cared far more about trying to make a microscopic theory of superconductivity, be the person to find it, understand superconductivity, than he did about having discovered the transistor.
Bardeen and Pines showed that as electrons move through a metallic lattice, the combined influence of their interaction with each other and with the discrete modes of atomic vibrations called phonons can sometimes lead to a net attractive interaction between the electrons. Bardeen, along with fellow physicists Leon Cooper and Bob Schrieffer, then turned those insights into a microscopic theory of superconductivity. Named after its originators, the BCS theory explained how, below the transition temperature, electrons pair up and no longer scatter off the phonons. The result? Resistance disappears and the material becomes superconducting. The BCS theory was a major breakthrough and won John Bardeen his second Nobel Prize in physics. Yet despite this, it took scientists until 1986 to discover a new class of superconductors with significantly higher transition temperatures. not ordinary metals, but more like ceramics, these so-called high-temperature superconductors were far cheaper and easier to cool. But they behaved quite differently, and the conventional BCS theory failed to explain their superconducting properties. In a flurry of research, scientists worldwide raced to come up with a new theory. David Pines joined in also, turning to the methods he had learned from his former teacher, John Bardeen.
My approach to this problem was very much influenced by the way Bardeen had gone about solving superconductivity in ordinary metals. So that before trying any serious theoretical calculations, I spent my first 3 years or more working on this problem, just trying to understand at a phenomenological level what was going on.
The carbon lines are rather broad.
Just down the hall at the University of Illinois, Charlie Slichter had been employing a technique called nuclear magnetic resonance to probe certain bizarre magnetic properties in the high-temperature superconductors. After analyzing the data with graduate student Philippe Mantoux, David Pines boldly guessed that the magnetic interactions due to the spins of the electrons might play a key role in the superconductive state. This idea, which Pines termed spin fluctuation superconductivity, had been dismissed by his colleagues as an idea that would never work.
We were marching to a different drummer. We took a different point of view toward seriously trying to solve this problem than any of our colleagues.
To determine if they were on the right path, Philippe Mantoux was given the task of solving a complex set of equations called the Eliashberg equations. These describe the strong coupling effects associated with spin fluctuations. Pines and Mantoux felt that in using approximations to solve these equations, their colleagues had been led astray.
People had thought that they could cut through some of the difficulties by making some simplifications. And so we decided not to do that, but that was a lot easier to say than to do.
Employing NCSA's Cray YMP supercomputer, Pines and Mantoux were able to solve the equations in detail. Their results have been the first to yield superconducting transition temperatures as high as those found by experiment.
It's not as though we were the first people to do these calculations. We were the first people to do them right, to do them at the level of detail that is required to tell you whether or not the mechanism works. And that's where the supercomputer came in.
So far, the Mantoux-Pines spin fluctuation theory has held up as experimental data continues to confirm its predictions. After more than 40 years at the forefront of the field of superconductivity, at an age when other scientists might be thinking of retirement, David Pines is doing perhaps his greatest work.
To me, it's a source of joy and delight to be working very much at the frontier and perhaps making the most significant contributions of my career when I'm in my 60s. So it's a wonderful feeling.
For decades, scientists have used computers to model reality. Models which could only be represented as graphs, equations, or long lists of numbers. Thanks to dramatic advances in computation, scientists today can experience their models as dynamic pictures and sounds. However, fully unleashing the computer's power of representation can take more than a scientist's knowledge. Often, it requires an artist's touch. In fact, there's a growing demand in science and industry for interdisciplinary experts mastering both computation and representation of the results. Yet there are few schools to provide the integration of art and science that's needed. So where can students learn and build their skills? And where can industry tap their expertise? At NCSA, this need is fulfilled by the Renaissance Experimental Laboratory. Envisioned and piloted by computer artist and university professor Donna Cox, the REL has become one of the nation's preeminent classrooms dedicated to the art of scientific representation.
The day is coming when we all will be our own directors and script writers and be able to speak out to the world using these technologies in very innovative ways that will bring together, I think, new art forms and I think new scientific discoveries.
The REL is a crossroads for students and scientists, engineers and artists, sharing ideas through images and sounds. In the REL, a computer provides a window into the structure of complex data. Scientific concepts are turned into animations and conveyed to broad audiences. New media forms are tested for their power to provide insight into data and engage the imagination.
Well, my course is a very unusual course. It's one of the few on campus that students get art and design credit as well as undergraduate and graduate computer science credit. It's a very interdisciplinary course. I would say about 60% artists and designers, about 30% computer scientists and engineers, and the rest is other musicians and Unix hackers and all sorts of people who come with their special individualized skills.
An engineering student in the Renaissance Lab, Joe Lomar is creating an animation for the Exploratorium Science Museum in San Francisco.
I think that it's very important to have the collaboration between artists and scientists, since the scientists will look at something very cut and dry and not look at the representation.
Through the REL, Joe became a consultant for Caterpillar, an NCSA industrial partner. In developing his computer graphics skills and applying them to real-world problems, Joe aims to become a better engineer. The career benefits for Joe are clear. Caterpillar also benefits from the technology transfer facilitated at the laboratory.
There is a need to be able to change the corporate world by using this technology to help with the research and the development and to streamline and make more efficient the types of research and development that corporations are doing today.
Gaining widespread recognition for their technical skills, many REL students continue after graduating to apply their expertise and inventiveness in a professional research environment. These visualizations of acid rain were created for the Environmental Protection Agency by REL graduate Chris Landreth.
How do you represent a time series of data that may take up 10,000 nodes over a three-dimensional space? How do you represent that in a way that a scientist can immediately figure out what's going on? And that is where we have to deal with issues of visual composition.
An average protein has about 5,000 atoms. A 5,000 atom protein is immense and too complex to understand from simple-minded mental analysis. So what aids this analysis is a computational and graphical visualization tools. Seeing is believing. And so being able to see an object, a protein, move in real time, move in real dimensions that you can visualize and conceptualize and manipulate gives us a large handle on understanding how these proteins function.
Shankar Subramaniam, biophysics professor and NCSA research scientist, is collaborating with Donna's class on the visual representation of life's master molecule, DNA.
We are interacting with Professor Donna Cox, who is a tremendous asset to us in being a graphics expert and who in addition is a great computer artist. And we are interacting with her in bringing to the classroom an element of art and science where the boundary between the two is nebulous, and yet it gives us profound insights into the scientific principles.
Building on its success, the REL plans to incorporate novel technologies to stay at the leading edge. High-definition imaging, virtual environments, and a teleclassroom reaching audiences nationwide. All will tighten the coupling between science and the imagination.
To a large extent, the direction that I see visualization going is to touch upon humanity. There's a statement, data is not information, is not knowledge, is not wisdom. I think with the development of software, hardware, and our ability to perceive what we can use with this combination, we're going down that direction, from data to wisdom.
This visualization represents the simulated behavior of perhaps the most mysterious and invisible phenomenon in the universe, the black hole. Some black holes are thought to form when massive stars collapse under their own gravity. Others are thought to lurk at the violent center of certain galaxies, including our own Milky Way. Regardless of how they might form, black holes exert gravitational forces so powerful, not even light can escape. These exotic objects were first predicted from a simplified solution to Albert Einstein's most famous theory, his general theory of relativity. Yet Einstein's theory remains largely untested. Its equations are so complex that even now, 75 years after their introduction, no one can solve them in their full generality.
The Einstein equations are sort of the Mount Everest of theoretical physics. And you know, we want to get to the top.
Larry Smarr and the scientists, students, and visiting researchers of the University of Illinois' Gravitation Group are solving the Einstein equations through the study of black holes. But rather than using purely analytical methods, Smarr pioneered the use of numerical solutions to analyze the problems, creating a new field of study called numerical relativity.
Effectively, the only way to do the science of Einstein's equations is to build a numerical laboratory in which we create artificial universes and then with computers go in and do experiments on them. You can't put a black hole in a laboratory.
Given the complexity of these numerical problems, Smarr and group leader Ed Seidel have employed the most powerful supercomputers to help tackle the challenge. Their goal is to solve increasingly complex numerical black hole problems, using these as building blocks toward a general solution of the Einstein equations.
We want to study the black hole case instead of some other space-time because there are a lot of interesting dynamics going on there that will be important when we try to study the Einstein equations in their full generality.
The first step in developing the necessary computational techniques was to solve a highly idealized black hole problem, that of a single, non-rotating, distorted black hole. Group member David Bernstein was given the task of writing a computer code to solve this previously unsolved problem.
There were really no very reliable solutions to, what you'd expect a non-rotating, distorted black hole to do, during its evolution. No one had even done that problem. What's interesting about the stuff that we did with the single black hole is that essentially for the first time we can get pretty accurate solutions of pretty wildly distorted black holes and their whole evolution.
It's become the basis for the rest of the work we do. Every time now we go into a new area, we constantly want to see, do our results reduce to the single distorted black hole that David Bernstein was working on?
Seidel then enlisted visualization expert Mark Bayuk for a journey into the invisible world of black holes. Together they created computer animations comparing Bernstein's distorted black hole data with previous data on two black hole collisions. By actually seeing a black hole evolve in simulation for the first time, Seidel was able to make some important discoveries.
We really learned from those animations that the two black hole collision is very similar in a sense to a single distorted black hole, at least at the late stages. And maybe the surprising thing is it doesn't take very long for those two black holes to form a single black hole that then oscillates just like a single black hole.
And it is these oscillations that may eventually provide the physical evidence that helps to prove the existence of black holes, and perhaps even verify Einstein's theory.
Einstein's theory allows you to calculate what would happen if you perturbed a black hole in some slight way. And you can calculate, if you were to perturb a black hole by tossing a stone into it, for example, that it would respond in a very definite way. It would start to oscillate at a frequency that you can calculate. And then that frequency, or that oscillation, will send out gravitational waves that could be detected.
Although gravitational wave detectors are still not fully developed, the group hopes to have a catalog of theoretically calculated waveforms ready when the instruments do come online. This will aid scientists in their ability to identify the detected waves. To do this, the gravitation group is adapting its codes to run on the newer, massively parallel supercomputers, such as the Connection Machine 5.
What we want to do is to build a code that will run on the CM5, the current one, but that machine is scalable. So in a couple of years, when that machine is much larger, more powerful, we'll just be able to grow our problem.
If you take a rock in orbit.
Larry Smarr and the rest of the gravitation group foresee a time when the experimental and theoretical sides of relativity come together. a time when Einstein's famous general theory of relativity can be both solved theoretically and verified experimentally.
When we get to the point that there really are experimental results in relativity, and there are routine codes to solve the Einstein equations, and here we're talking early in the next century, then we will finally have a true science of general relativity.
If you would like to know more about the activities featured in this program, please contact NCSA at the following address.